Let's look at how to use tf.math.approx.max.k, in which what essentially we'll do is we'll create a dot product of two tensors and then find the top k values in each of the rows of the output matrix or output tensor. And for that, the example that we are going to use is coming from the docs. I've added a couple of values to it. So let's create a tensor x that is equal to tf.constant, and in this tensor this is going to be a 3 by 4 tensor with values 1 2 1 5. Then we have this, that's going to be our first row. Then likewise we'll have two more rows. So let me go ahead and copy the cells, paste them here, and the values will have a value of 5. Then we have 6, 1 and 5, and then in the last row we'll put the value of 1 for all of them. So these are all 1. So that's the x, and then likewise we'll have another tensor which is y. So we'll change this name to y, and the values for these are 1 1 4 1 in the first row. So this will be 1 1 4 1 in the first row, and then in the second row we have 1 6 1 1. So I'll change this to 1, 6 remains as is, change this to 1, and in the last row we will leave the ones as they are. So once we have created these two, the next thing we'll do is create a function that's directly from the docs. We'll create a function for maximal inner production search MIPS, and for this we'll use the decorator at tf function jit underscore compile is equal to true, and def mips x comma y comma k is equal to 2 because we are looking at top 2. The maximum of the top two values or the first two values, and we'll calculate dists is equal to tf dot einsum einsum, and we'll look at what this is after we run this cell. Ik, so dimensions of the ik, that's dimensions of one matrix, and then we have the dimensions of the second matrix. So ik comma jk, and then this will result in a matrix that has dimensions ij using x and y. And there are two ways we can get the output. One is dot underscore product comma idx is equal to tf dot math approx underscore max underscore k, and we specify dists comma k is equal to k, then return dists dot underscore product and idx, so the index of the maximum values, and then we can call the MIPS x comma y is in k is equal to, let's say k is equal to 1. We have specified here default value as 2, but while calling we are using k is equal to 1, and then we'll put the output values that come out of this in the variable dists dot underscore products neighbors, and then we can print the values. So let's, for printing we'll simply say print this, then we have on a new line we have the next one which is dot underscore products, and then on the next line we have neighbors, neighbors, neigh neighbors. Okay, and now when we run this we get an output. We should get an output with the three tensors. So the first one is what the dot product the dot product is of the two x and y. And then in the second tensor, what we have are the maximum values. So if we look in this first row, in the top, among the first value, let's say the top value, the maximum value is 1, which is right here. In the second case, the maximum value again is 47 among the top two, and then here the maximum value is among the top two is 9, and the index location for all of these is 111. If we change this MIPS to, let's say, a value of 2 and now run this, in this case what we get are two values. So we have the 19 followed by 12, then we have 47 followed by 20, then we have 7 followed by 9. Likewise, if we put 3 there, then we would get the entire set, all the values, uh, essentially from largest value to the smallest value. So that's how this is working. Now, going back to the EI and sum, what we can do is we can try and create an example. So let's copy, or we could use the same set of x and y values. Let's say we print np dot x comma y, and so y, the value we have this as 3 by 4 and this is 3 by 4, so we'll use a transpose of y, and that will give us one dot product, and then we can get the same values by using tf dot tensor dot x comma y dot transpose, and here we need to specify additional axis argument uh, to get the final output, and uh, this we can always convert it back to a numpy array like so. And finally, yet another way we can get the same output is by using matrix multiplication, matmul x comma y transpose. And now when we run this, there's an error. Let's see where the error is. We have np dot okay, so eager tensor has no attribute t, and that's okay, yep, right. So what we can do is we can convert this to numpy. Let's convert this to numpy and convert this to numpy, and now run this. And so let's see, tensor dot what's the error? It has no attribute t. That's, I think the reason is because we are using tensors in all of these cases. So what I'm going to do is copy this entire thing and paste it here, and we'll convert this to an array, uh, uh, or I'll leave this as is and convert this to array by typing numpy in front of this array. So this should now be okay if we remove this and that. So let's run this. So here's the output we get. We get a similar output in all the three cases, which is the dot product of all of these three. And if we want to again check really quick one of the values, we could do that. And so that's going to be, if we take essentially what we are trying to do is we are taking each of these values and multiplying it by these values. So we have, once we transpose this, so if you look at y transpose y dot t, uh, this is what we have. So 1141, that's what we are multiplying this with. So we are say this is going to be 1, then we have 1 1, and then we have 4, and followed by another 1, 1141, and this output is 13. And okay, let's see where we went wrong. 1141, So that, and let's look at the value for x. So we are essentially multiplying 1 multiplied by 1, 2 multiplied by 1, then 1 multiplied by 4, and 5 multiplied by 1. So just all of them are multiplied by 1 except 4, and so that's what we have. Oh, so my mistake, this should have been multiplied by, and so we get a value of 12, and that's the value of 12 we have right here. So that's how the Einstein sum is working in this case, which we have used here. Another variation for using TF dot math dot approx max k is we could use the TF dot nn. So let's copy this, paste this here. I'm going to comment out this first line, and instead of math we are going to use nn. Rest of it stays the same. Now when we run this, we should still get the same output as we did before. So what approx max helps us do is it returns the maximum k values and their indices of the input operand in an approximate manner. And the next video, what we'll do is we'll look at how to get the approx min k. But just before we end the video, there is one final note that I wanted to make, and that is if we have we create a tensor. Let's say we create tensor m0 is equal to tf dot random dot normal with a shape of 2 by 3, and we create another such tensor. Let's call this tensor m1 with a different shape which has a shape of 3 by 5. And now if we perform the sum, if we say tf dot I in sum, and we say ij comma jk, and the resultant is going to be hyphen the arrow ik, and the input is going to be m1 m0 and m1. And then if we look at the shape of k, if we look at just the e, what we get is the output. This is the output we get. So we have 2 by 3 and 3 by 5, that the output is 2 by 5. And so these are 2 rows and we have the 5 columns right there. That was it for this video. I hope in this video you got some intuition about how to use the approx max k method in the TensorFlow math library. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I hope to see you all in the next video. Thank you.